All right, let's dive into something pretty mind-bending today. We're going to be tackling the double-slit experiment, which is like one of the most famous and most puzzling experiments in quantum mechanics.
Yeah, it's a classic for a reason, you know?
Yeah,
It really makes you question how things work, like down at the smallest level.
right, like at the subatomic level.
Exactly, yeah.
Okay, so for those who maybe haven't encountered this, what is the double-slit experiment?
So imagine like waves in a pool,
Okay,
and there's this barrier with two openings, two slits, and you can see those waves spreading out, overlapping. You get those peaks and troughs.
that interference pattern.
Exactly, interference. And now let's replace the water waves with light. What do you think we see?
Well, light acts like a wave, right? So I'd guess we'd see the same interference pattern on the screen behind the slits.
Right, you got it. Bright bands where the waves reinforce each other, dark bands where they cancel out.
Yeah.
Classic wave behavior.
Makes sense. But now let's switch it up. Instead of light, we're going to fire tiny particles, like little grains of sand, at the two slits. What would we expect to see on the screen now?
Well, if you think about how particles behave, they're kind of like tiny bullets, right? Each one going through one slit or the other.
Right, like straight through.
So you just end up with two piles of sand behind the slits.
Yeah, exactly, like two distinct lines. Okay, so that's what classical physics would predict. But here's where things get a little strange when we enter the quantum world. Instead of sand, let's fire atoms at the slits. What did scientists think would happen when they first tried this?
Initially, they figured, well, atoms are particles too, just like grains of sand, so they'll behave the same way.
Hmm?
You'd expect those two clumps of atoms on the screen, right?
Right, following that same logic.
Yeah.
But that's not what happened, is it?
No, not at all.
So what did they see?
They saw an interference pattern, just like the one created by the light waves. Somehow, those tiny atoms, the building blocks of matter, were acting like waves and interfering with themselves.
Wow, okay, that's already blowing my mind a little bit. How on earth did they try to explain that? It's not like the atoms are coordinating with each other, right?
No, definitely not. So they thought, well, maybe the atoms are somehow bumping into each other,
Yeah.
interacting as they go through the slits. To test that, they sent the atoms through one at a time, making sure there was no way they could interact.
So each atom was like on its own little solo mission through the slits?
Yeah, exactly.
And what happened?
They still got the interference pattern. Even with individual atoms, each atom somehow knew about both slits and still contributed to that wave-like pattern on the screen.
Okay, now that's really strange.
Yeah.
So it's suggesting each atom went through both slits at the same time, even though that seems impossible. So if it's not the atoms interacting, what is it?
Yeah, that's the big question, right? To try and figure it out, scientists decided to add in the idea of observation. They wanted to know which slit is each atom actually going through.
So they tried to like catch the atoms in the act, like set up a tiny camera to spy on them or something.
Not a camera exactly, but they set up a detector near one of the slits.
Okay,
It would basically tell them if an atom went through that slit.
so they were like trying to pinpoint its path, catch it red-handed.
Yeah, basically.
So what happened when they turned this detector on? Did it solve the mystery?
Well, this is where things get even weirder. When the detector was on that interference pattern on the screen, it vanished.
Wait, so the interference pattern just disappeared?
Gone. Completely. Instead, they saw two distinct clumps of atoms, just like you'd expect if the atoms were acting like little particles.
Hold on. Just by observing which slit the atom went through, they completely changed the outcome of the experiment?
That's right. It's like the act of observation itself forced the atoms to behave like particles instead of waves.
That's wild. Okay, so it's not the detector itself that matters, but the act of observing. What if the detector is there but not turned on?
You're getting it.
Yeah.
Now we're really getting to the heart of it. They did exactly that. They left the detector in place, but turned it off. So the atoms would still pass by it, but the detector wouldn't actually record which slit they went through.
So the atoms are like passing by thinking, hey, maybe someone's watching, even though no one actually is.
Exactly. And guess what? The interference pattern came back.
No way.
Yeah.
So even though the detector was off by it, the atoms still acted as if they were being observed, and that wave-like pattern reappeared?
Yep. Pretty mind-blowing, right?
This is beyond mind-blowing at this point. Does this mean atoms are somehow conscious? Like they're choosing how to behave based on whether or not they're being watched?
Well, that's a question that's still up for debate.
Yeah.
Some interpretations suggest that our consciousness might actually play a role in shaping reality at the quantum level.
So reality is like this fuzzy, undefined thing until we look at it.
It really challenges how we think about the world. And
Hmm.
this whole idea of things being connected, even when they're separated by distance, brings us to another fascinating phenomenon called entanglement.
Entanglement? That sounds like something out of Star Trek.
It kind of does sound like science fiction, but entanglement's real. It's been proven over and over again.
Okay, so then what is it? How does it actually work?
Imagine like two particles, they're linked somehow, and they share the same fate, no matter how far apart you separate them.
So you mean like if I do something to one particle,
The other one instantly changes too.
even if they're like across the universe from each other?
Yeah,
Yeah.
exactly. It's pretty crazy.
That's insane. Okay, so we've got wave-particle duality, the observer effect, and now this entanglement thing. What does all of this even tell us about reality?
It's telling us that things might not be as set in stone as we think, you
Hmm.
know? It challenges our everyday experience of how things work and opens up a whole new world of possibilities.
So it's like the universe is full of all these hidden connections and possibilities that we don't even realize are there.
Yeah.
Okay, well, this has been an incredible journey so far, I have to ask. What are the practical implications of all this? If we can actually harness these quantum phenomena, what kind of technologies could we create?
That's a great question. And it's something that scientists and engineers are working on right now. One of the most promising areas is quantum computing.
Oh, yeah, quantum computing. I've heard that term thrown around. What
Man.
exactly is that?
So instead of bits, the zeros and ones in our regular computers, we'd have qubits. And qubits can be both 0 and 1 at the same time. That's because of something called superposition.
Superposition. What is that?
Think of like a coin spinning in the air. It's both heads and tails until it lands. That's kind of like superposition.
Ah, I see. And how does that apply to quantum computing?
Well, it allows these quantum computers to do calculations in a completely different way. They can explore many possibilities simultaneously. It gives them a huge boost in processing power.
So are you saying these quantum computers could solve problems that our normal computers can't even touch?
It's exactly. Problems in medicine materials, science, artificial intelligence cryptography, things that would take our current computers billions of years to solve a quantum computer could do it in minutes.
So like designing new drugs with incredible precision or creating unbreakable encryption codes, is that what you're talking about?
Exactly. The possibilities are truly mind-blowing.
It sounds like we're on the verge of a technological revolution then.
We are. And it all started with this simple experiment. Two slits and a beam of atoms. It just shows you the power of curiosity and how much we still have to learn about the universe.
Well, this deep dive has definitely left me with more questions than answers, but that's a good thing, I think. It sparked this sense of wonder and a desire to learn more.
That's the beauty of science. It's a journey of constant exploration and discovery.
Speaking of discovery, here's something for our listeners to ponder. We've talked about how observation affects quantum systems, but what exactly is an observer? Does it have to be a conscious being, like a human, or could a machine or even another particle be an observer?
That's a tough one. It really gets at the heart of what consciousness is and how it relates to the physical world.
It's a question that might not have a clear answer, but it's definitely worth thinking about.
Absolutely. It reminds us that we're part of something much bigger than ourselves. And there's still so much we don't understand.
Well, I think it's safe to say that the double-slit experiment has shown us that reality is far stranger and more mysterious than we ever imagined. Thank you for joining us on this journey into the quantum realm.
It's been a pleasure.